So we have reached a very important part of our lecture, which is beam deflection. So when we deflect a beam, we know now we deflect it from the neutral axis, we develop stresses, but we need to figure out what is the amount of that deflection. So we need to develop an equation that relates the deflection at every point along the beam. So we're going to follow a very, very similar procedure. So we are going to look at essentially here curvature, and we're going to relate it to that, basically that deflection that we see here, d theta ds. We can use small angle approximation, and then we can relate this change in that angle to our other parameters here. One quick note that E times I is our flexural rigidity. It's a very, very important term, and we'll see that a little bit later. But we're going to solve beam deflection in this class using the Euler-Bernoulli equation. So basically, it's a fourth order ODE, where Qx here is the load in general. It's a general distributed load, but we can model point loads as well. And we also see that our bending moment is proportional to the second derivative of our expression for that deflection, v of x. So bending moment is proportional to the second derivative. Our shear moment is proportional to the third derivative. These are really, really critical expressions that we need to know, and we need to generally commit to memory, because again, we know that to calculate stress, it is going to be proportional to that bending moment. So if we're trying to find regions of maximum stress to see if our material will fail, that is going to be critically important. So we have fourth order ODD, we need 4 boundary conditions. We're going to use Mathematica, you bet you. But to do this, we're going to have to, again, rely on our basics here. So let's talk about some boundary conditions for beam bending, because it's all going to be about developing boundary conditions. So if I have a cantilever beam or fixed beam here, I know that at x equals 0, there's going to be no deflection, and then there's going to be no change in slope there. At the opposite end, I'm not going to have any restoring, basically bending moment or shear moment. If I have pin supports, I know that my deflection is going to be 0. There will be a resultant shear force there, but I will not have any restoring bending moment. So those are really key critical boundary conditions that you can use to solve a lot of the problems that we're going to see in this course. So you're going to have to rely on the basics, and we're going to have to solve these ODEs and then see if our expression makes sense intuitively. So we'll do that next time for a simple end-loaded cantilever beam. See you then.